Hello all. With this lecture, we begin our new course. As the name suggests, we will be actually dealing with the necessary mathematics or the necessary calculus part of mathematics for business and social sciences. Right. So, we will be touching only the fundamentals. We are not much into the deeper theory parts. We will be handling with a little fundamental concepts and their practical applications in a peripheral sense. So, we begin our course with the most fundamental concept, equations. So the word equation is something used to come into someone's mind when we hear the name mathematics itself. So what do we actually mean by the word equation? Right. See, from the word itself, it carries out a sense that there is something being equated, or we use a sense of equality. Right. We use this symbol to denote a sense of equality. So to be a little more formal, we can define an equation to be something in which two mathematical statements, say this is a mathematical statement, is equated to another mathematical statement. Right. So equation is something in which a mathematical statement is being equated to another mathematical statement. Right. So if we try to get an example, x equal to 5 is an equation where x is a mathematical statement and 5 is another mathematical statement. X square plus 9 is equal to 25 is another mathematical equation. X square plus y square plus 2z is equal to 9a plus b is another equation. We are actually trying to connect two mathematical statements with a sense of equality. Such a setup is called an equation. Right. So how many types of equations are there? Numerous. There are varieties of equations. Let's check a few of them. So what do we mean by a linear equation? Linear equation. So we have seen a few examples of equation. If all the terms in the equation, all terms in the equation are raised to the power of 1, such an equation may be called a linear equation. For example, x plus 7 equal to 25. This is a linear equation. A plus some 25 is equal to 35. It's another linear equation. But consider an equation x square plus 7 equal to 19. Obviously this is an equation, but this is not a linear equation. Why is it not a linear equation? The power of the term x is 2, not 1. For that reason, this equation is not a linear equation. The other both two equations are linear equations, since all terms of the equations are actually raised to the power 1. Right. So what is a linear equation? Linear equation is an equation in which all the terms are raised to a power 1. Right. So we will be sticking a little much onto linear equations for now. Before going to other types of equations and their properties, what do we mean by solving an equation, or what do we mean by a solution of an equation? So consider we have an equation. The equation may have variables, right? So solution can be defined as, for our sense, for our use, we define solution as a number, say a, whatever, a number. If substituted for the variable x, suppose our equation has a variable x, if a can be substituted for x such that the equation becomes an identity, or the equation becomes true, such a number a is called the solution of the equation. Right. Let's stick on to a little more concrete example. Consider an equation x plus 7 is equal to 9. For this equation, 2 can be identified as a solution, since if I can replace x with 2, the equation stands true. Right, or the equation will become an identity. Right. See, these things may seem simpler, you know, all these things from your fundamental classes or your basic classes of school itself. But as a part of our concern of completeness, we have to go through all these things. Right. So this is what we mean by the solution. Right. Is it necessary that an equation has a single solution? Is it necessary that an equation has a single solution? Consider an equation x square minus 1 equal to 0. Right. So x equal to 1 is a solution. X equal to minus 1 is another solution. So this equation has more than one solution. Right. So it is not necessary that an equation has a single unique solution. An equation can have more than one solution. And the set of all those solutions of an equation is called a solution set. Solution set. So what is solution? Solution is a number which can be substituted for the variable so that the equation stands true. What is a solution set? Solution set is the collection of all possible solutions of an equation. Right. Now, suppose we have two equations. I call them to be A and B. Okay, capital A and capital B. Let A and B be two equations, any two equations. Let S1 be the solution set of A and S2 be the solution set of B. Right. So what do we have? We have two equations and their corresponding solution set. So every number or every element in the set S1 is a solution of A and every element in the set S2 is a solution of B. Since S1 and S2 are solution sets of A and B respectively. So if we have S1 equal to S2, we may call the equations A and B are equivalent. Equivalent. So what are equivalent equations? Equivalent equations are those equations having the same solution set. Equivalent equations are those equations having the same solution set. Right. We have seen that an equation need not have an unique solution, but there are a little more interesting concepts like here. Suppose we consider the set of all real numbers. Say we have an equation A and the solution set of A happen to be the set of all real numbers. What does that mean? Sometimes this may happen. Some equations have their solution set as the set of all real numbers, which means any real number is a solution of that particular equation. So, shall we think about an example? Consider the equation 0 times x plus 1 equal to 1. Right. 0 times x plus 1 equal to 1. This is an equation. Obviously, this is an equation. There are two mathematical statements which are connected by means of an equality. Right. So, can you think about the solutions of this equation? See, if you replace x with any possible number, any possible real number, you will get the equation standing true. Right. See, since whatever the number, if you multiply with 0, the term will go to 0 and what we have left here, 1, which is obviously equal to the right hand side. So any real number can be replaced for x keeping this equation true, which means any real number is a solution for this equation, or in other words, the solution set of this particular equation is the set of all real numbers. In such a case, such an equation is called an identity. So what is an identity? An identity is an equation whose solution set is the set of all real numbers. Right. So there is another extent for this solution set situation. Now we have seen the case where the solution set happens to be the whole real number system. There are some situations where the solution set is empty, or in other words, the equation does not have any solution in real numbers. In real numbers, can we figure out something? We have a famous equation x square plus 1 equal to 0. We know that this cannot be solved in real numbers. The solution exists as a complex number, but for this case, we consider only the set of all real numbers. Okay, so the solution set of this particular equation is empty in real numbers, since it does not have any solution. Similarly, if we go to a little more simpler things, say x square is equal to minus 17. Can the square of any number, can the square of any real number be a negative number? No. The square of any number has to be either 0 or positive. So this equation has no solution, or the solution set of this particular equation has to be empty, since no real number can replace x successfully holding this equation. Right. So these are examples of for the case the solution set is empty. So that was the story of equations. We have seen linear equation, and we know what do we mean by solutions, solution set, identity, and we have seen that it is not necessary that an equation always possesses a solution. Right. Now we are thinking a little more about equations, about graphing an equation. Right. So graphing is actually a pictorial representation of an equation. Before proceeding to graphing, we need to learn a little about Cartesian coordinate system. Cartesian coordinate system. So what is a coordinate system? See, we have a plane here. We have a plane here. I mark this point as A. I mark this point as B. Right. It was my very choice to select these 2 points. If I ask another guy to mark 2 points on this plane, that fellow may mark these 2 points. Right. If I ask you to mark another point, you may obviously mark these 2 or some other points. Right. So there is no standard strategy to distinguish between 2 points or uniquely determine a point. Right. Here we introduce the coordinate system, which actually enables us to uniquely determine a point on the plane. In fact, not just on the plane, on the space or any dimensional space, but we basically concentrate on the plane. Right. So how does the Cartesian coordinate system works? So remember, we use the Cartesian coordinate system to uniquely identify a point on the plane. Right. So we have a setup here. The Cartesian coordinate system consists of 2 lines, 2 straight lines. One is placed horizontally and one is placed vertically. There are 2 lines, 2 straight lines, which elongates infinitely to both directions, which means these 2 lines goes on to infinity on both directions. Right, this does not end anywhere. And these 2 lines are set perpendicular to each other. These 2 lines are set perpendicular to each other, which means they are set at an angle of 90 degrees. Right. We call this horizontal line to be x-axis, the vertical line to be y-axis. Again, let me remind you that these are the fundamentals you have already learned from your schools itself. But for the sake of completeness and for our necessity to be applied in our concept, we again revisit these things. Right. So this is the setup of Cartesian coordinate system. And there comes the fundamental question, how do we use this setup to uniquely identify a point? Right. Suppose we have a point here. We have a point here. We can mark 2 points on the coordinate system or the coordinate lines, coordinate axis. We call this together as axis, and the center point where these two axes meet is called the origin and denoted with the letter O. Right. So we have a point here, I call that as A. I have drawn a line which is parallel to y-axis meeting the x-axis. Another line parallel to x-axis meeting the y-axis. These lines actually gives us distances. This line gives the distance to the point A from x-axis. I call that to be x. Sorry, I call that to be y. And this is a convention. So before moving on, let me start with here itself. Suppose the distance from x-axis to the point is y, and the distance from y-axis to the point to be x. Then the point A may be denoted as x, y. Right. There is a reason that we take this as x. We are moving along x-axis in x units to reach the corresponding point of this point, and in the same way we are moving y units in the y direction to reach the corresponding point of our point A. Right. So the point A can be uniquely determined as a pair x, y. Right. So is it unique? Is there any other point on this plane with this coordinate x and y? No way, since if you travel x distance in this positive direction of x-axis and y distance in the positive axis of y-axis, we will reach at this unique point. Right. So that's how we determine a point on the plane uniquely. So I have mentioned that this is the positive direction of x-axis. This is the negative direction of x-axis, this is the negative direction of y-axis, and this is the positive direction of x-axis. These two lines together split this plane into 4 pieces. One piece here, the other piece here, we have 2 more pieces here. So this plane actually splits the entire plane into 4 pieces. We call them the 4 quadrants. The 4 quadrants. This piece of plane is called the first quadrant. It's a convention. This piece of plane is called the second quadrant. This is the third quadrant, and this is the fourth quadrant. Right. Now, see, what could be the signs of x and y on these quadrants? Are they always positive everywhere, or are they always negative everywhere? We have thought about a unique representation. When I said you that move x distance from origin in the x-axis, you can move in this direction or you may move in this direction as well. You have the freedom to move backwards. Right. So suppose we are moving x direction in the other side of x-axis. Right. So if you follow the same convention, we may find a point here which we may have to represent it as xy itself. But then the uniqueness may be countered, and as a part of the convention we choose this to be negative x. Everything on the left of origin is considered to be negative on the x-axis. So this point will be negative x, y. Y is in the positive direction. Right. So you may follow this convention to mark any point on any quadrants. You are very much familiar about this. Let's again check out something. So what could be the sign of x and y in these quadrants? In the first quadrant, second quadrant, third quadrant, fourth quadrant. Right. So in the first quadrant x is positive, y is positive. In the second quadrant x is on the left side of origin, so it's negative. Y is still upward of origin, so it may be considered as positive. In the third quadrant x is to the left of origin, so it is negative. Y is downward of origin on the y-axis, so it is again negative. On the fourth quadrant x is to the right of origin, so it is positive, but y is to the downward side of origin, so it is negative. So on the first quadrant both x and y are positive. On the second quadrant x is negative and y is positive. On the third quadrant both x and y are negative, and on the fourth quadrant x is positive and y is negative. Right. So this whole setup is called the Cartesian coordinate system. Right. So what is Cartesian coordinate system in a few words? It's actually set up with two lines. One is horizontal and the other is vertical, which are set perpendicular to each other and elongating into the infinities on both directions. We can mark any point on the plane with the help of this system. Right. That's all about Cartesian coordinate system. We will be using this Cartesian coordinate system throughout this course to graph or to represent any point or any function. Okay, now we are all set to graph a linear equation. Right. So we will use this Cartesian coordinate system to graph a linear equation. Before proceeding, why do we call an equation linear? We have seen the definition that an equation having all its terms raised to the power 1 is called a linear equation. Why is it called a linear equation? So that makes sense here. The graph of a linear equation will be a straight line. The graph of a linear equation will be a straight line, and for that very reason we call such equations as linear equations. Right. So how do we graph a linear equation? We graph those linear equations which are in x and y having two variables, right? So suppose we have an equation of the form y plus 7x plus 9 is equal to 12. We can try to graph this equation or make an attempt to graph this equation or these types of equation. In short, we will be graphing those equations in two variables, and the two variables, obvious reasons we will be using here will be x and y. Right. So we graph equations in x and y. So we have seen that the equation of a graph or a linear, the graph of a linear equation is a straight line that can be of any slope or in any direction. So as a general line, I choose this to be the graph of an equation. Okay, choose this to be the graph of an equation. What does this mean? We have points on this graph. Say this is x1, y1, this is x2, y2. Right. So what do we mean by this graph? Suppose we have an equation y equal to some ax plus b, right, some ax plus b, or y plus ax plus b equal to some 7 or some constant, another constant, say c. So say we have such an equation. In that case, if we have a point x1, y1 on the graph of this equation, that means we can successfully replace x and y with x1 and y1 without violating this equation. Or in other words, x1, y1 forms or if x1, y1 makes this equation as an identity. Right. So if we have any equation, any linear equation, we can find such points, and the collection of all those points together constitutes the graph. Right. So the graph is actually all those points on the plane which makes this equation an identity. Right. So how do we practically draw the graph of an equation? especially of a linear equation. Right, how do we draw the graph of a linear equation? We'll be better convinced if we go with an example. But before moving to an example, I need to explain something other than this. So suppose we have a graph like this. This graph meets x-axis and y-axis at two different points, obviously. So this is our x-axis, this is our y-axis. On x-axis, the y-coordinate is 0. So we have the general form of points on the x-axis as x0. The y-coordinate is 0 means we are not moving in the y direction, we are only moving on the x direction, right? Similarly, on the y-axis, we are not allowed to move in either directions of x, but we are only restricted to move on y-axis. So the general form of points on y-axis is of this form 0, y. The first coordinate or the first part of this pair was x coordinate and the second part was y coordinate. The x coordinate of all the points on y-axis is 0. Right. Similarly, the y coordinate of all the points on x-axis is 0. Now, the point at which the graph touches the y-axis is called y-intercept. Y-intercept. And the point at which the graph touches x-axis is called x-intercept. So what are y-intercept and x-intercept? X-intercept is the point at which the graph of an equation touches x-axis, and y-intercept is the point at which the graph of an equation crosses y-axis. Right. So y-intercept is on the y-axis. So every y-intercept will have its first coordinate or the x as 0, and every x-intercept is on the x-axis, and for that very same reason their second coordinate will be, or the y-coordinate will be 0. So we make use of these intercepts to draw the graph of an equation. We first find the intercepts and mark them on the graph, and we join them together with a straight line to find the graph of, or to draw the graph of an equation. Right. So the strategy is find the intercepts, join them with a straight line. Right. So let's go to an example if possible, so that things will be a little more clear. So before proceeding to graphing, we need to discuss a little more about the slope intercept form. So what do we mean by slope? So with the layman's meaning or the literal meaning, it actually gives us a slope of the line. We have seen that the graph of a linear equation has to be a straight line, and obviously a straight line will have a slope. See, consider this line and another line of this one. Right. The second line seems to be a little more steeper than the first line, which means it has a higher slope or a greater slope. And what about this line? This is less steeper than both other lines, which means this has a smaller slope. Right. So the slope here carries the usual meaning of slope, and intercept means what we have seen just now. Intercept means the points on the axis through which the graph passes through. Right. So we can rewrite an equation using this slope intercept form, or the slope intercept form of a line is y equal to mx plus b. Right. Where m is the slope of this line, we'll explain what is slope later, and b can be found as 0, b is the y-intercept. Right. If 0, b is the y-intercept and m is the slope, then the equation corresponding to that graph can be given as y equal to mx plus b. Right. See, there is an issue here. We are actually moving in the backward direction. We'll be explaining these things later. For now, just remember the names, or you might have seen this before. And we are not explaining this in the proper order. Our textbook suggests this order, but this may be a little more discomfort for the learner as well as the teacher. But for the sake of completeness, you just remember these names. Right. So now let's try to graph a function, I think.